All right, welcome to the deep dive. Today we are diving into something pretty fundamental. We're going to be exploring the connections between time, space, light, and gravity.
Okay.
At first glance, these might seem like totally separate things. Space is where stuff exists, right? Time is just what we measure with clocks. Light lets us see, and gravity is what keeps us on the ground. But what if I told you that they're all actually deeply interconnected, like different aspects of the same underlying reality?
Right. And, I think it's pretty natural for us to sort of think of them separately when we first start thinking about it. We have these basic understandings of them, right? Space is just like that empty area all around us. Time is just like our experience of moments passing by. But when we start digging a bit deeper, and that's exactly what we're going to do in this deep dive, we'll see that these concepts are much more intertwined than we might initially realize. We're going to draw on some fascinating explanations, like this really interesting conversation I came across between a science teacher, Mr. Thompson, and his student, Miss Lynn, on a fictional podcast called Exploring the Universe.
Oh, cool.
They really break down these concepts in a way that's easy to understand. Our goal is to basically unpack all of that for you today and really see those connections clearly.
I love it. So let's jump right in. And I think the first mind-bending idea we need to wrap our heads around is that space and time are not actually independent. They're actually fused together into this single four-dimensional entity.
Yeah.
We call space-time.
Space-time.
Yeah.
It's a really fundamental shift in how we perceive reality, right? We tend to think of the world as this three-dimensional space, and then time is this separate thing that's constantly flowing. But the idea of space-time is that these two are actually woven together.
Right.
Into this unified fabric, kind of like a stage on which the entire universe is playing out.
I like that. Yeah.
And Mr. Thompson in that podcast uses this great analogy to explain it. He talks about space-time like a giant trampoline.
Okay.
It helps us to visualize it a bit better, instead of just thinking about it abstractly.
Oh, for sure. I remember when I was first learning about this stuff, I think, just like Miss Lynn in the podcast, I thought of space as like just the empty area around us, and time is what clocks measure.
Right.
It's so basic. But then when you start thinking about space-time as this unified fabric, everything changes.
Absolutely. And this trampoline analogy gets even more interesting when we bring gravity into the picture. We all know what gravity is, right?
Yeah.
Keeps our feet on the ground. But how does it fit into this idea of space-time as a fabric?
Yeah.
Miss Lynn asks that same question in the podcast, and that's where the analogy really starts to shine.
Okay.
So imagine this. You've got the trampoline, right?
Yeah.
That represents space-time. Now, put a bowling ball on it. That bowling ball represents a massive object like our sun.
Okay, I'm visualizing it.
The bowling ball doesn't just sit there on the trampoline.
Right.
It creates a dip, a curve in the fabric.
Right.
And this is where things get really cool because gravity is not some mysterious force that's pulling things in.
Right.
It's actually the curvature of space-time itself that dictates how objects move.
Whoa.
So think of the Earth like a smaller marble rolling on that trampoline.
Okay.
It's not being pulled in by the bowling ball directly. It's following the curve that the bowling ball has created in the trampoline.
So the Earth isn't being actively tugged on by the sun?
Not in the traditional sense. The Earth is just following the path of least resistance through this warped space-time.
So it's more like a guide than a pull.
Exactly.
That is so wild.
And that brings up a really interesting question, right? Because if gravity is just the shape of space-time, then why do we feel this pull?
Yeah, good point. Why do we feel it?
Well, the feeling of gravity, that pull down, is our body's way of interpreting the fact that we're constantly trying to move along these curves in space-time.
Right.
We're always being guided by the shape of space-time, and when that path is constrained, like when we're standing on the ground, we feel that as a pull.
Okay. It's like the ground is pushing back up on us.
Exactly.
Wow. And if that wasn't a big enough mind shift, right? We also have to consider that this very fabric of space-time, it doesn't just affect how things move through space, it also affects the passage of time itself.
Right.
This is where the concept of time dilation due to gravity comes in.
Yeah. Time dilation is one of the most fascinating consequences of general relativity.
Oh, yeah.
And it means that time is not this constant tick-tock that's the same for everyone everywhere.
Right.
The rate at which time passes actually depends on the strength of the gravitational field you're in. So the stronger the gravity, the slower time passes.
So time is relative.
Exactly. It's not absolute. It's
Yes.
relative to where you are and how strong gravity is in that location.
I'm trying to wrap my head around that.
Yeah.
So, like, if you were standing near a black hole where gravity is incredibly strong,
Yeah.
time would pass much slower for you than for someone who's far, far away in space.
That's right. Mr. Thompson uses this great thought experiment in the podcast to illustrate this. He imagines two people.
Okay.
One is hanging out near a black hole,
Okay.
and the other is way out in deep space where gravity is very weak.
Okay.
From the perspective of the person in deep space, time would appear to be moving much slower for their friend near the black hole.
Wow. That is mind-blowing.
It is.
So time, something that we experience as so linear and consistent, is actually flexible.
Absolutely.
That's wild. And there are real-world examples of this, right?
Yeah, there are. A great example is astronauts on the International Space Station.
Oh, yeah.
They actually age slightly slower than us here on Earth. And that's due to a combination of their speed and the slightly weaker gravitational pull they experience up there.
So it's not just like a theoretical thing.
Nope, it's a measurable effect.
That's crazy.
It really highlights how time is not just this immutable backdrop. It's an integral part of the fabric of space-time, and it can be warped and stretched by gravity.
Right. And by motion, too, you're saying.
Exactly. And that brings us to our next big player in this cosmic drama.
Okay.
Light.
A light.
Light plays a really crucial role in all of this.
All right. So tell me about light.
Well, light is often called the ultimate speedster, and for good reason.
Okay.
It travels at an astonishing speed.
Right.
About 300,000 kilometers per second.
That's fast.
That's incredibly fast.
Right.
And here's the kicker. That speed is constant for all observers, regardless of their own motion.
Really?
Yeah.
So if I'm like zooming through space in a spaceship,
Yeah.
light would still appear to be traveling at that same speed.
Exactly. It doesn't matter how fast you're moving, light will always appear to be traveling at that same constant speed.
Wow.
And this might seem counterintuitive, but it's one of the cornerstones of Einstein's theory of special relativity.
It's hard to wrap your head around, right? But it's true.
It is.
So what does this constancy of the speed of light tell us about space and time?
It tells us that space and time are not absolute, but they're relative. And what I mean by that is, in order for the speed of light to remain constant for all observers, regardless of their motion, space and time themselves have to adjust.
Okay, I think I'm following. So like if I'm moving really, really fast, time would actually slow down for me.
Yeah, exactly. And distances would appear to contract.
Wow.
These are the mind-bending consequences of special relativity.
That is mind-bending.
And they're all rooted in the fact that the speed of light is this universal constant.
So light isn't just what allows us to see.
Right.
It's actually a fundamental part of the fabric of space-time.
It is. Mr. Thompson, in that podcast, actually describes light as a ruler that helps us measure and understand the geometry of space-time.
A ruler. Okay.
Because its speed is constant, we can use light to gauge distances and time intervals across the vast expanse of the universe.
So how does gravity affect light if light is part of this fabric of space-time?
Yeah, that's a great question. And the answer lies in a phenomenon called gravitational lensing.
Okay.
Have you ever heard of gravitational lensing?
I've heard of it, but I don't really understand it.
So basically what happens is when light passes by a very massive object like a galaxy or a black hole, its path gets bent.
Okay.
It's as if the massive object is acting like a lens, bending the light around it.
So light doesn't always travel in straight lines.
Well, it does, but the space-time that it's traveling through is curved. Remember our trampoline analogy?
Right.
Imagine rolling a marble across the trampoline near the bowling ball.
Okay.
It's going to curve.
Yeah.
It's the same with light. It's always traveling along the straightest possible path, but that path is curved because of the massive object's gravity.
Wow. That's so cool.
And this bending of light, this gravitational lensing, it's more than just a cool phenomenon. It's actually a really powerful confirmation of the connection between gravity and space-time.
Okay, I'm trying to put all of this together.
Uh-huh.
So we have space-time, which is this unified fabric.
Right.
We have gravity, which warps space-time.
Exactly.
Time, which is flexible and influenced by both gravity and motion.
Yes.
And light,
Yeah.
which is this constant speedster that's also affected by the curvature of space-time.
You got it. And what's really amazing is that all of these seemingly separate concepts are actually just different aspects of the same underlying reality.
So it's not just space and time, it's space-time. It's not just light traveling through space, it's light revealing the shape of space-time.
Exactly. And this interconnectedness, it's not just the theoretical curiosity, it has really profound implications for how we understand the universe.
Right, so this is more than just like an interesting idea. It actually helps us understand how the universe works.
Absolutely. It's the foundation of modern cosmology.
Yeah.
It helps us understand everything from the orbits of planets to the evolution of galaxies to the behavior of black holes.
Wow. So, to quickly recap the journey we've taken together today, we've seen how space and time merge into space-time, how gravity is not a force but a curvature of space-time, how time is flexible and influenced by gravity and motion, and how light reveals this curvature and helps us understand the very fabric of the universe.
Exactly. It's a lot to take in, but I think it paints a really beautiful and awe-inspiring picture of the universe.
Absolutely.
And it leaves us with a really profound question to ponder.
What's that?
If time is flexible and space is malleable, what are the implications for our understanding of the universe's history, its future, and our place within it?
Wow.
And if these seemingly fundamental aspects of reality are so interconnected, what other aspects might be more fluid than we currently perceive?
That's a great question to leave our listeners with. Lots to think about.
It is. The universe is full of mysteries, and the more we learn, the more we realize how much more there is to discover.
It's an incredible journey of exploration, isn't it?
It really is.
And that's what we're all about here on The Deep Dive. So thank you for joining us.
Thanks for having me.
It's been an incredible conversation. Until next time, keep exploring.
Keep wondering.